Hi class, welcome to PEP 288, Motor Learning and Performance with me, Elizabeth Harding. We are going to discuss Lab 4. So this was about the speed accuracy trade-off, or more specifically, Fitz's law. Fitz's law, which predicts movement time based on the size of a target and the distance from that target. So if you recall, you had 6 different tasks in which you put dots into different boxes that were different sized boxes which were a certain distance apart. So what you were to do was enter your data or the number of taps into our class data sheet. So here's a copy of our class data sheet. You can see I have our participant IDs in column A, and then for index of difficulty, so tasks A through F, we had 3 trials of each. So you were to enter your raw data, and then I believe I had calculated for you the median number of taps, right, for task A through F, and then from there we looked at the average movement time, and the average movement time was across the 3 trials. So for each participant you had an average movement time for A, B, C, and so on. From there we calculate the average movement time for the whole class, or in my case, I've done an analysis on 45 individuals, but the average movement time for task A, B, D, etc. So I went ahead and just copied my headers here so that it would set me up to make a really nice chart very quickly. So if I just highlight these 2 rows of data, my headers plus the mean values for tasks A through F, and going up to clustered column chart, there you go. You can see I've done a few of these so far. Right, and the first thing we're going to do is get rid of that. All right, so I have my tasks on the x-axis and my movement time in milliseconds on the y-axis. And remember, we calculated movement time in milliseconds by taking 10,000 over the median number of taps. And that gave us a very good estimate of movement time. So from here, if I just go to chart layout, I can enter a vertical axis. And make sure you put your units in milliseconds, and there we go. And so another thing that you can do, since you're essentially creating 6 different graphs on one chart, is go ahead and highlight just one of these boxes. So I just left-clicked here, but if I left-click a second time, it just highlights this ID equals A. And if I right-click on that one box and format data point, I can pick a color just for it. Right, and so you can do this in any pattern if you wanted to just print in grayscale, checkers, polka dots, whatever. It just tells a better story because these were 6 distinct tasks. And so if you left them all blue, it might be very confusing to your reader. And you can see what I did here, made this a little bit bigger. It's all color-coded. All right, so what does this all mean? It wasn't specifically stated in your lab assignment to create a graph, but this is definitely helpful when it comes time to discussing your results. Okay, so let's go ahead and go back to the results, or the assignment. So within the discussion, you were supposed to discuss how the results of this experiment that we did compared to what Fitz's law predicted should have been the results. So if I go back and look at my graph here, what Fitz's law states is that the distance between targets and the size of the target matters. Sorry, so I need to actually skip. Bear with me here. Okay, so this is movement time. This is a picture of movement time. Movement time equals A plus B, which are constants, times log base 2 of 2 times the distance over the width. So you can see that as the distance changes, right? Or as the distance becomes greater, the targets become farther apart, movement time is going to increase. As the width or the size of the target becomes smaller, because it's on the denominator, movement time is going to increase. And so you might have to go revisit your lab sheet that actually had the tests outlined for you, because I don't have them here. But you can see that when the index of difficulty is a 1.14, right, the reaction time or the movement time is going to be faster than, say, when the index of difficulty is higher, like a 3.24 or a 4.25. So I just went ahead and calculated those indexes of difficulties, indices, I think that would be the correct plural, indices of difficulty. Right. Well, here's an example of how I did that, actually. So for instance, in IDA, the boxes were approximately 5/8 of an inch wide, and they were separated by 11/16 of an inch. Right, so I did this in just a calculator using the natural log function. And this is just how you would do this in a calculator, since a typical calculator is log base 10. But you can use natural log, the ln, which most of us should have on our calculators, over the index of difficulty here, over the natural log of 2. And that'll actually give you a relatively simple calculation for index of difficulty, which in this case was, I believe, 1.14. And going back to my table, and it was 1.14 for A. So I'm not asking you to calculate the index of difficulty, so please don't get hung up on these values here. I just did it because I wanted to show you that Fitts' law, for the sake of our class, actually did a very good job of predicting movement time. Right? So as the index of difficulty increased, so did our movement times. Right? So I just wanted to point out one little nuance of this very crude formula for index of difficulty, which is this negative value here. So it's not necessarily the absence of no difficulty, right? The negative value, where it's super, super, super easy because it has a negative value. Basically, it's going to be negative because, or the index of difficulty will be negative because if the amplitude, or in our case, the distance, is less than half of the target width, it will show up as negative. And so here you can see that it is, in fact, less than half of the target width. So imagine it, or think about it in a relative state. So IDB should have the shortest reaction time because it would have the lowest index of difficulty compared to the other 5 tests. So it's not necessarily well, it's definitely negative, but it's not meaningfully negative, I guess is the right term. Sorry, that's very confusing. But that's all I'm really going to say about that. You don't necessarily have to talk on that at all. But here we go. It was the fastest reaction time, and it was also the, according to Fitts' law, was the easiest task. All right. So the other things that you need to discuss in your lab reports, you needed to give proof or give an example of how the group's results did demonstrate the speed accuracy trade-off phenomenon. So just choose 2 ID sets that describe the characteristics, and so just visually look. So if they were very, very far apart and the targets were very, very small, like in IDE, you would expect that the movement time would have been quite high, right? It would have taken a lot longer than, say, something where the targets were very wide and close together. Right? So how did your group's results demonstrate that phenomena? A little bit more challenging was, how did it not? So maybe visually look at something, or going back to your data sheet and looking at the tests. Was there something that you thought should have been easy but wasn't? And so give characteristics of the size of the targets, how far apart they were, etc. And then the last question I would like you to answer, and I'm really going to give you lots of freedom on this one, is just looking at a real world motor skill. So whether it's shooting a target, some sort of goal-related event, how could you improve somebody's or help, say, an athlete or a student improve their performance, exploiting Fitz's law? And, be very complete with your responses here. You describe the task. How would you increase the difficulty, for practicing? And how do you think that practice, that time spent in practice, would actually improve their performance? All right, so I will post these slides online, and if you have any questions, feel free to email me. Thanks.